More than 70% of the surface of our planet is water, and understanding where all that water goes and how fast it gets there has become a critical challenge. Hydrology is the science of water, and an important application of hydrology is flood modeling. Floods are among the most frequent and costly natural disasters worldwide. They can cause direct losses, such as damaging infrastructure and wiping out crops, but they also cause indirect losses, such as disruptions to businesses and the economy. For these reasons, it is important to be able to predict which areas on land are at risk for flooding and what conditions or rainfall intensities could cause that flooding. These types of forecasts can help save lives and limit the loss of property or goods. The science of flood modeling has been evolving rapidly, transforming what used to involve historical data and a bit of guesswork into a high-tech and data-driven approach. For many decades, flood modeling relied on what we refer to as historical frequency analysis. Scientists would look at past rainfall and river flow records to calculate the likelihood that a location would experience a 100-year flood, or a rain event that was projected to occur once every 100 years. This approach was simple and limited, but it formed the basis for many applications, including the provision of flood insurance. The problem with the historical frequency approach is that climate change has been tearing up the rulebook, so to speak. So a flood that was once a 1 in 100-year event may now occur once every 50 years or even once every 20 years. In short, we can no longer assume that the future will look like the past because our climate and planet are changing so rapidly. Luckily, two major advances in data and computing power are helping the modern era of flood modeling keep pace with the changes occurring on Earth. First, from a data standpoint, we have moved beyond simple river gauges and now rely on technologies like lidar, or light detection and ranging, from aircraft, drones, and satellites to provide high-resolution digital elevation models, or DEMs, of the terrain. These models are crucial as they show us exactly where water will pool and how fast it will flow across the land. Second, remote sensing satellites are now continuously monitoring other weather-related variables like precipitation, soil moisture, and even changes in river width that can provide near real-time insights into a river basin's capacity before the rain even hits the ground. Together, these advanced data sets are fueling advanced hydrodynamic models that can better show how and where water might move over the Earth's surface. The most transformative change, though, is the integration of artificial intelligence, or AI, and machine learning into these hydrologic models. Traditional physics-based simulations might take hours to run, which is too slow to be useful in the event of a flash flood. AI models, trained on vast historical and simulated data, can make highly accurate predictions of flood extent and peak flow in seconds. This near instantaneous speed is vital for informing the early warning systems that are used to help keep people safe. For instance, Google developed an AI flood model that extended reliable flood forecasts in data-scarce regions of the world by 2 days, providing a crucial advantage for evacuation and preparation. Hydrology is no longer just about measuring rainfall. It's about predicting the complex behavior of water in a rapidly changing climate. Advances in geospatial data science and AI, though, are giving us tools to better protect people and communities.